Aircraft engine noise in and around airports are an undesirable part of airport operations and adversely impacts the quality of life in the surrounding communities. Part of its mission to improve the quality of life, the NASA Glenn Research Center in Lewis Field plays an important role in the development of technologies to reduce aircraft engine noise. The development of successful noise reduction strategies relies heavily on understanding the mechanisms and characteristics of engine noise. A principal source of noise in modern commercial aircraft engines is the impingement of fan wakes on the downstream exit guide vanes. This noise, often referred to as rotor-stator interaction noise, is produced in discrete frequencies called tones as well as broadband frequencies. Tones are generated at regular frequency intervals determined by the blade passing frequency or BPF. To better understand the rotor-stator interaction noise characteristics, it is necessary to measure the levels of interaction tones. The rotating rake system, developed at NASA Glenn Research Center, is a unique tool for measuring the rotor-stator interaction tone levels. The rotating rake system was developed in the Advanced Noise Control Fan Facility. The ANCF is a 4-foot diameter low-speed fan that replicates the relevant features of turbofan engine tone noise in a controlled environment. The combination of the easily modified duct assembly with the rotating rake system has enabled rigorous evaluation of the utility of the rotating rake system. The rotating rake is shown here in the exhaust plane of the ANCF in order to measure the noise that propagates to the far field. The use of the rotating rake system in the ANCF rig represents a low technology readiness level, or TRL, application of the system. The rotating rake can be deployed at various locations in the fan duct inlet and exhaust in order to measure the internal propagation of the noise field. This can be particularly valuable in evaluating and verifying acoustic prediction codes. The rotating rake system works as follows. The rotational speed of the rake is set at an exact fraction, usually 1/100th of the fan speed. In the case of ANCF, that is, 15 to 20 RPM depending on the speed of the fan. This synchronization of rotational speeds is the enabling principle of the rotating rake system. The rotation imparts a unique Doppler shift on the frequency of the measured acoustic fields, separating the acoustic field components into slightly different frequencies. This display of an online measurement from 2 of the rake microphones illustrates the separation of the acoustic components. Each vertical line represents a different component that can be analyzed independently. In the stationary frame, these components would be the same frequency and therefore indistinguishable to the observer. The rotating rake has been extensively used in the NASA Glenn 9x15 wind tunnel for fan models that are more representative of actual turbofan engines. These fans rotate at much higher speeds, so that the rotation speed of the rake is usually set at 1/200th of the fan speed, or up to 60 RPM. The use of the rotating rake system in the wind tunnel represents a medium technology readiness level, or TRL, application of the system. Having been proven in the laboratory and wind tunnel settings, the rotating rake has been used to measure the acoustic characteristics of a production turbofan engine, the TFE 731. This successful engine test was a demonstration of the utility of the rotating rake system at a high TRL level. Using diagnostic technology such as the rotating rake will enable designers to create quieter engines, helping to meet the noise goals set for 10 and 25 years in the future. Ultimately, objectionable aircraft noise will be contained within the airport boundaries.